Hi, welcome back to the hydrogen NMR spectrum. Let's briefly go over the spectrum again. The typical value first, then some of the variations. First, 0 to 4, you get the sp3CH. And those hydrogens with all carbon hydrogens attached to it, they normally give number around 1 ppm. But if you start to attach electronegative atoms, the hydrogens start to get de-shielded and move to the downfield as the hydrogen gets more de-shielded. So as you have a chlorine level of electronegative atom on the alpha carbon, then you get about 3.0 ppm. And two of them make the alpha hydrogen de-shielded like 5 something ppm. And three of them make the hydrogen de-shielded to 7 point something, and they're still sp3 carbons. And that should be the guideline because the oxygen is more electronegative than the chlorine, so you expect the alpha hydrogen will shift it more downfield than the alpha hydrogen with the chlorine, so you expect that to be around 3.5. Then regular alkene hydrogen comes normally between 4 to 6, and then aromatic ring has a exceptionally strong anisotropic effect to move down to the 6 to 8. And then aldehyde peaks around the 10. Rarely observed, but sometimes you see hydrogen on oxygen around 12. But most of the OHs and NHs are showing up randomly anywhere. But those broadness can be a hint whether you have OH-NH or regular CHs. And normal CHs have sharp signals as a singlet or multiplets, depends on the neighbors. So the chemical shift is indication of how close your interested hydrogen is to the electronegativity, or how close it is to the double bond, and so on. We can say that NMR gives you 4 different types of informations. First, the X value, chemical shift. That's proportional to the electron density, as you know, in the reference of TMS. Number 2, the integration. That's proportional to the number of hydrogens. So separate sets of number will be given on top of the each peak to tell you number of hydrogens. 3, splitting of each signal. That is going to tell you about the number of neighboring hydrogens. Number 4, number of signals. This tells you how many different types of hydrogens, not necessarily number of hydrogens, but different types of hydrogens. And that is determined by symmetry. So the hydrogens with the same symmetry will give one same signal all together. yet that particular signal can be splitted into number of small peaks due to the neighboring hydrogens. Then the overall area under those splitted signal, you get the integration for it to tell you about the number of hydrogen that are same kind. Then those hydrogens' location on the x-axis will be determined by the electron density that gives you the idea of the environment. So this is a typical hydrogen NMR, how it looks like. And you have one peak at 0. So that is actually from the standard TMS, tetramethylsilane. Okay, so we tune the instrument using TMS. But besides that, you see 1, 2, 3 signals. That's what I mean by number of signal, different types of hydrogens. You have 3 different types of hydrogens in this compound. And then the location of hydrogen will tell you which ones are closer to the electronegative atom, such as C is very close to the electronegative atom, and this one here is around 4, so this hydrogen, this type of hydrogen is very close to the electronegative atom, probably is alpha hydrogen, and that one's somewhat far away from the electronegative atom, right? So you can see their environment in terms of electronegativity caused by causing the electron density, shielded or deshieldedness of the hydrogen. Then you can see this signal out of 3, right? This particular signal has 3 lines, so splitted by neighbors. And this also splitted, but in different number, meaning this one has a different number of neighbors. And this is not splitted, and it's kind of broad. Okay, so that is the typical looking of HNMR. So we talked about chemical shift. And as you know, the number on the X, you roughly know, the electron density caused by what type of environment, sp3, sp2, or sp, and so on. And then the integration will be written, and that gives you number of hydrogen. So there is nothing much we can do for non-majors, because the number is not always the real number of hydrogen. Like I said before, it is just the ratio. And then the splitting pattern, we deal with n plus 1 rule. If the neighboring hydrogens have about same partial charges, right, then you can say you count number of the neighbors, and that's n. Then you add 1, that's the number of lines. So let me give you an example, right? So you have CH3 and the CH2, and you have a chlorine. You know that the alpha carbon has 2 hydrogens, and that's most deshielded. Therefore, it goes more downfield. And you remember that's around 3.0 ppm. The next one is beta hydrogen. roughly speaking, for non-majors, you can say that is about 50% of the alpha hydrogen value. So roughly speaking, 1.5 ppm. It's more shielded, so somewhat less plus charge. That means you are expecting your NMR runs from 0 to 3. Okay, so you are expecting this hydrogen gives a signal around here, 3 point. Normally it's like a 3.2 or 3, but let's just say 3.0 ppm, and about 1.5-ish you expect another peak. Okay, let's label it hydrogen A, hydrogen B, hydrogen A, hydrogen B. So you know chemical shift. Then secondly, you have to show integration. The integration is number of hydrogen, right? So 2 hydrogen for hydrogen A type, so it should be 2. The area under the curve has to be 2, so let me put it here, 2 hydrogens, and the peak B is for 3 hydrogens. Then the splitting, that's what I'm trying to tell you, right? N+1 is the rule. So for A, the neighbor is B, and there are 3 of them. So you say 3 plus 1, 4. So the A gets 4 lines. So it's a quartet. 4 lines with the 2 hydrogen area. So 1, it should be normally symmetrical, same gap. So same gap, symmetrical with the 2 side lines smaller, 2 center ones taller. There is a certain rule called the Pascal's triangle, but we'll skip that for now. Then for B hydrogen, those 3 hydrogen, right? That has a certain electron density more than A. That's why those hydrogens showing signal here, but it has 2 neighbors, so 2 plus 1, this has 3 different energy states caused by the 2 neighbors. It's like both are excited nuclei that makes this neighbor feeling a certain energy. When both are low energy alpha spin, it feels somewhat less, energy from the neighbor. When one is alpha, the other is beta, it's the middle of the 2 extreme, so the neighboring hydrogen feel different energy. So 2 of them causing 3 different energy level for this neighbor. So this neighbor gets 3 lines, but that 3 lines should have the same splitted gaps, and also the area under the curve I'm trying to draw should be responding to 3 hydrogens, 50% more than this, so a little taller. Like my drawing is not really spaced out well, that has to be same as this. So those 2 signals, and nowadays we don't use TMS anymore, but okay, here you may see TMS. So we got the splitting pattern and integration, as well as a chemical shift. You are able to draw out the NMR. What happens if you have same alkyl group, but you have now fluorine? So how many signals you are expecting? how many types of hydrogens you have. Again, it's going to be same. These two are same type, right? Same amount of charges. Also in the space, you know, on the tetrahedral carbon, those two hydrogens are identical. Those three are also identical. So you have one and the two types of hydrogen. So you expect two signals, okay? Number of signals, two types. So two signals, like 1, 2 signals. Then chemical shift wise, now you're looking at more downfilled, de-shielded hydrogens, around 4, because you have a fluorine. So around 4, you're gonna have alpha hydrogen showing absorption. And then here, that's A, right? Then the next one is about half of the 4-ish, so close to the 2-ish for the B. So A and the B, because it's possessing less positive charge and less de-shielded and more shielded than the other hydrogen. So you are expecting the two signal here with the same splitting pattern, because the number of neighbors are same and the integrations are same, right? 2 and the 3. So the pattern should be same number and should be something like that. I'm trying to make a point that if you change the neighbors, only that, then everything else is the same except the chemical shift is changing. Okay? That's good enough for you. But in reality though, I did a little lie here, because fluorine is also active in NMR, and it has a quantum number of half. So this has an alpha and the beta spin, creating two different energy level for these neighbors. And then fluorine's influence is very big. So the closer hydrogens get more influence and split into two different levels. And this one also get influenced by the fluorine. So this also gets two sets of same peaks. So in reality, you get another quartet, and that's made by the fluorine. And here you get another triplet, also made by the fluorine. Then, you know, this is close to the fluorine, so they are more apart, okay? And this is far away, so influence is small, so the numbers are more similar, so they are closer. Another thing for the major students, you know, the halogens, those electronegative atoms as well, their influence to the alpha and influence to the beta, they're not always going by the order of the electronegativity. Yes, oxygen influence alpha very strongly, but they don't influence beta as much as chlorine does. Okay, even between halogens, fluorine influences the alpha very much and de-shield them very much, but fluorine does not influence the beta as much. So the 50% rule for the beta hydrogen doesn't really apply well for the fluorine. Okay, normally this value come around 1 point something, close to 1 point something, not quite 2. Okay, 1.2 or something. But for the chlorine beta hydrogen, they are more influenced by chlorine, losing more electron. So although this has a less electronegativity, the beta hydrogen on this molecule seem to be more de-shielded than the one near the fluorine. Okay, this has to do with the molecular orbital, but for non-majors, you don't need to worry about this. I think this is enough. You don't even have to be aware of those couplings by the fluorine. Just be aware of the power of the electronegativity, and then able to catch the chemical shift is increasing as you have a more electronegative atom, and that should be enough. All right, let's tackle this molecule. First, how many signals do you expect for this compound? Basically, how many different types of hydrogens you have. Okay, by look, you know you have this one, this methyl group, different from others. Over here, you have CH, that's different from others. But those two methyl groups, what do you think? If you rotate this single bond in the tetrahedral geometry, right? If you have a regular line, wedged line, then you have a hydrogen that's a wedged, that's dotted line. If you rotate, you can basically exchange these two, and you can make indistinguishable, so they are identical. Or you can use a mirror that goes through the molecule, okay? Then you can make these two identical. So we can say you have type 1, type 2, and type 3 hydrogens. So you expect 3 signals. How about chemical shift? Because we start to see many different types of CHs of sp3, let me give you a guideline here. If you have CH2, let me use different color because I make it busy over here, I think. CH2 without anything attached to, theoretically, it should be giving you about 1.2 ppm, right? Then whenever you add more hydrogen here, right, you deduct about 0.3 for adding hydrogen. So deduct 0.3. Why do you deduct it? Because if you have a more hydrogen on the carbon, hydrogen's giving electron to the carbon, right? So the carbon is getting more electron rich. Therefore, these hydrogens, compared to before, it's getting a little more electron. So it's more shielded. So the number decreases by 0.3. Okay? And other adjustment you need to remember is when you put electronegative atoms on CH2, you deduct, you add, because you are removing electron density, right? You are removing it. So you add about 2.3 for one oxygen. So if you have oxygen, the alpha hydrogen will be 1.2 plus 2.3, so about 3.5 when it's a CH2. What if it's a CH? Then, because you are losing hydrogen, it should be opposite to that, right? Therefore, you should add about 0.3. And if you add hydrogen and the oxygen, the net change would be, like this case, you have a 3 hydrogen, not 2, and you have oxygen. Then you deduct by 0.3 and you add 2.3. So overall, you're adding 2.0. So this must be around what? 3.0 ppm. Okay. But this one has lost hydrogen. So you add 0.3, so 1.5. Then you have oxygen. So roughly 3.8 ppm. Because you're losing hydrogen, it got more than this. Then this carbon has 3 hydrogen, not 2. So you're adding it. So you deduct. So it should be about 0.9. But you are near oxygen. It's not alpha. So you don't actually add 2.3. But you cannot ignore oxygen. It's close enough. So what we actually do is you're adding about 0.3 for beta oxygen. Okay. So overall, it will be about 1.2 ppm. Like I said, chlorine, bromine, their influence to the beta hydrogen is much greater than that of the oxygen and the fluorine. So oxygen and the fluorine is about 0.3, 0.4. But if you have a chlorine, bromine, you are adding here 0.6, twice more influence on the beta hydrogen, okay? Therefore, let's check our rough thumb of rule thing for the non-majors. If your alpha hydrogen next to the oxygen, I say about 3.5. You see that? They're around the ballpark. If you have to decide which one is more de-shielded, then you decide the carbon with the more carbon rather than more hydrogen, because you have a more electron. You have more electron with the more hydrogens, right? So the carbon with the more hydrogen getting more electrons. So you can say 3.5-ish, but little less, little more. That should be enough for non-majors. And then the beta ones, about half of it. So about 3.5. Half of it is like 1.7, you know, it's not close enough. But because NMR is relying not only on the chemical shift, but other thing as well, your dependence for the chemical shift is not as serious as other spectrum like IR. Okay, IR, you only rely on X number, then you add some of the things like intensity, Y value, or shifting. That's also chemical. That's also X value. So your decisions is heavily, it's not all, but heavily on X value. But on NMR, this rough estimation most of the time it's good enough for you if you're non-major. So you don't have to remember these influences of on the alpha carbon, alpha hydrogen, or beta hydrogen, and so on. All right then, so we are looking at 0 to about 4 ppm, and we are expecting A here around 3.0, and then B around 3.8, then about 1.2 we are expecting C. Then you know C has 6 hydrogens, so your integration, right, number of hydrogen should be 6 hydrogens. Then A must be 3 hydrogens. That's the area under the peak. It's not proportional to the height, but roughly speaking, you can say that. B, one hydrogen, very small. Okay, so when you are drawing the height 6 to the 3 to the 1, but a note you have to make here is when you have multiple signals, right, you have many peaks, meaning the height, as you have more and more splittings, they're like, inverse relationship. If you have more splitting, in order to show same integration with more splitted peaks, each little lines making that peak should be shorter. Okay. Therefore, height is not always matching with integration, especially when you have multiplets, more than couple splitting, right? Unless you have a doublet or triplet, you should not go by height as a measure of integration. Therefore, let's tackle C has how many neighbors to think about splitting? C has only one neighbor, right? So the C, according to the n+1 rule, one neighbor, so C must be doublet. So 2 lines to show 6. So one line probably represent 3 hydrogens. So I don't really make the 2 separate peaks. This is one signal and 2 little lines with the spacing. Okay. Then the B has 1 hydrogen. So already 1/3 of this peak. I said one peak here is representing, roughly speaking, 3 hydrogens, because 2 lines represented 6, right? So if it's one line, it's already 1/3 of it. However, how many neighbors you see for the B? You have 3 and 3, total 6 neighbors. So 6 plus 1, 7 lines. So 7 lines altogether must be 1, which is 1/3 of it. So each line of the 7 here should be very tiny. So again, in the 7 line structure, you have to put the middle one tallest, then the side one less, and then the side of the side even less, that kind, right? So 1, 2, 3, 4, 5, 6, 7, something like that. Almost invisible. Looks like it's a noise. If this was an IR spectrum, you say this is a sp3ch, but this is a noise. But it's not the case for NMR, so be careful. Then A, right there, 3 hydrogen. So it should be equal to this one single line. Then this has how many neighbors? Neighbor has no hydrogen, so 0 plus 1, 1 line. That means this has to be as tall as one of the lines here. And there you go. That's your ether compound NMR HNMR spectrum, including all the 4 informations together. Let's try this ketone compound. So many hydrogens, 12 hydrogens. What do you think? This oxygen is de-shielding all these hydrogens, but on the alpha carbon, you don't have any hydrogen. So you don't have any peaks around 4, 3 point whatever. You don't see that, like A and the B in the previous example. You have beta. Okay. This beta carbon has no hydrogen, but this one does. 3 hydrogens. Then you have a gamma. Gamma, you can consider that like they don't have an influence of the oxygen at all. That's fine, okay, for non-majors. So what do we do? Well, this is the beta. So the value should be half of it, roughly speaking. The alpha with the oxygen could have been what? 3.5-ish, right? So half of it is about 1 point something. But in reality, this is about 2.1 or 0 beta hydrogen. That's because oxygen is sp2 hybridized oxygen, more electronegative than sp3 oxygen. Also, you remember the carbonyl group has a double bond. So anisotropic effect is making this hydrogen feeling more local magnetic field. So the energy gap between alpha and beta spin increases. So that pushes up to the 2 point something, close to 2.0. It almost never is lower than 2.0. Okay, that's because of the double bonded oxygen. And this one here, it's like a CH3. So remember, CH2 is about 1.2. If you have one more hydrogen, it should be more de-shielded. More shielded. So it should be about 0.9. Less than 1 is enough. Okay, so you can say, roughly speaking, around 0.9 ppm. Then you have found one type of hydrogen, and these three methyl group, 9 hydrogens, they're all identical. First, as you spin around this single bond, those 3 methyl groups are interchangeable. Okay, and among those individual methyl groups, you can also have those 3 hydrogens identical as you spin around the single bond. In fact, in the solution, this single bond, that single bond, they're always rotating around, feeling about same magnetic field. So you have 9 identical hydrogens basically. Okay, so all of them making one signal, the gamma. Therefore, on the spectrum, I don't show TMS anymore. You expect to see some signal up to 2.0, is 2 point something, so 2.0. There you have a beta hydrogens, and there around 1.0, slightly less than, still slightly less than that, you see gamma hydrogens. The gamma hydrogen has how many neighbors? No neighbors, hydrogen, right? So no neighbor, singlet. And there are 9 hydrogens. So very tall, singlet especially. All 9 hydrogens shows same absorption. So 9 times, remember? Like your IR. You have so many same CH stretching, sp3 CH stretchings. You got the tall signal, same thing. You have the same CH bond 9 times of the concentration of the molecule. So absorption is big, and that's integration concept right here. Then you have 3 of them. So 1/3 of it. See how many splitting you have. If you have more splitting, then you have to make it even shorter, right? So you see the neighbor and you're looking for it, there's none. So again, one line, so 1/3 of this. And singlet. So simple. With so many hydrogens, you have such a simple HNMR. Okay, you got less hydrogen but much more complex with this other example. Look at this example. If they give you IR data, this will be a lot easier question. But let's practice without IR. Okay, let's analyze the formula first. You have C4 with oxygen. As we all know, oxygen don't change number of hydrogen. So you are looking for the corresponding alkane formula. 2 times 8, 2 times 4 is 8 plus 2 is 10. So you gotta have 10, but you have 8. So you are missing 2 hydrogen, therefore your degree of unsaturation equals 1. Okay? Meaning what? You have either double bond or a ring. If it is double bond, it could be carbon-carbon double bond or carbon-oxygen double bond. That's it. The rest of them, they're all They're all alkanes. But from the chemical shift, you can already guess something. These 3 hydrogens showing 1 signal, right? And it is around 3.5. What does that tell you? You can make up a nice table, but let's do that when problem becomes complex. Okay, and on the test, if you're taking MCAT or GRE, most of the time you don't have that amount of time for organizing data that way. All right, so 3.5, and you see the oxygen. So this CH3 is already next to the oxygen. You can find that fragmentation already, as if you are doing mass spec. You got the jigsaw puzzle piece right there. And this one here, it's near 2.0, and you have another oxygen. All right, can this be on this oxygen right here? Can you connect it here like a CH2? No, because then you are alpha to the oxygen, so the ppm should move to the more downfield. So that's not the case. So no. What is it then? That's typical number. I told you that when you have a CO double bond, then this hydrogen, the beta to the sp2 oxygen, is close to the 2,0. It's really common, so it's very useful if you memorize this. Okay, normally the beta is about half of the value for the alpha hydrogen, but when it's sp2, it's a little more, so it comes up to the 2 point something. There it is. And how many hydrogens you have? The integration tells you there are 2 of them. Okay? Then what does it say? There are 4 informations on the NMR. You saw 3 different hydrogens, so type of hydrogen. And you saw chemical shift. So we got this information, being beta to the oxygen double bond. 3, integrations. So we applied it. Last information we didn't use yet is neighbors. How many lines you have? 4. That means n plus 1 is 4, therefore n, which is neighboring hydrogen, is 3. So you have neighboring hydrogen 3. Then you must have this on the NMR. Okay, could it be that? Well, then this cannot be a singlet because that guy has 2 neighbors. So you're looking for the signal representing 3 hydrogen of integration, 2 neighbor, so triplet. You're looking for a triplet with a 3 integration right there. Okay, this case you had only 3 signals, so you didn't have to do this thinking, but it's better if you get used to it, because on the real test you're gonna have many similar signals anyway. Okay, Then I said alpha, beta, gamma. Gamma is almost same as nothing. So you have a signal around 1 ppm ish. So perfect, you're done. You found one piece, the other piece. There was a one piece. Do you have how many ways you have to connect them? I believe there's only one, right? This can only get attached to that. We did this kind of job with the IR and the mass spec, so by now you should be able to do this easily, right? You have now this one connected to that, and then this. So if you have IR, what data you look for is the ester, right? So the ester carbonyl group is around 1735-ish. You look for that. And also intense signal for this partial double bond due to the resonance, 1200, 1300, that kind. And then here you expect around 1000. Then the rest signal is all sp3ch stretchings and vibration, bending vibrations, right? So you could do it without IR. Since the taping going longer than I thought, let's pause here, and I'll come back with the third video for non-majors dealing with the other functional groups. So I'll see you soon.